So I was finding out where we left off the
Hello, sir.
Yeah, please come again.
I was finding out where we left off our last meeting.
This is our next one. This is where we are supposed to continue.
Okay, so we're supposed to discuss this briefly, which I'm sure you have looked through. It's a solved problem, so once you apply your understanding to it, you will surely get the results as also arrived at. Yeah, so basically we have the figure here, which shows the electromechanical system with the required dimensions. So the magnetic core is made up of cast steel whose DH characteristic curve is shown in this figure. That's 1.9. So this is a BH. That's basically your flux density versus the field intensity. Okay, characteristic curve. That's what we have here. So emphasis is on the cast steel, and the coil has 250 turns. So this is our coil, 250 turns, and the resistance is 5 ohms. So R is 5 ohms. Okay, so for a fixed air gap length, okay, so this is our air gap. Okay, so air gap. So air gap length, which is fixed, as 5 millimeters, right? And a DC source is connected to the coil to produce. So this is a DC source, like plus minus. As far as this source is concerned, is direct current. So that with that we produce a flux density of 1 Tesla in the air gap. Okay, so the flux density of 1 Tesla is produced in the air gap. Alright, if that is the situation, let's find the voltage of a DC source. What's the voltage? And we should also find the stored field energy. Okay. Yeah, so basically that is what we had to do. Well, that is what has been done with this question. Okay. Right. It's very important to pay attention to the dimensions, okay, so that basically you're going to have 10 centimeters as far as the depth is concerned, and then if you like the length here 10 centimeters, which for your knowledge in engineering drawing, you would realize that this is 10 centimeters, and it's also expected that when you measure here, you also get 10 centimeters. And the same applies to the depth, so that this will be 10 centimeters, okay? And when we also consider this side, which is maybe the movable part, is also 10 centimeters in terms of depth, not the whole height, okay? With regards to your engineering drawing dimensioning concepts. So also you need to take note of the edge here, which is 5 centimeters. This simply means that the same 5 centimeters will be repeated here, okay, 5 centimeters, and then also If you look at this place also, the same thing, 5 centimeters, and then here too we expect 5 centimeters. That is to say that if I should have, anyway, I use my pen to do like that. So this place will also be 5. Okay. I'm going to have 5. So 5 centimeters. Also, the same applies to this area also. Okay, so we also have 5 centimeters. That is this, and maybe that's. So, if you like, we're going to have 1, 2, 3, 4. Okay, then you also have 5 centimeter here, so that the same thing will be also, this 5 centimeter will also be repeated here. I hope you are with me.
Absolutely, sir.
Yes, sir.
Yes,
All
sir.
right.
Yes.
So we will need to get the dimensions clearly to be able to determine, if you like, the total area of the core. Very important, or the length. Okay, very important because you will need it. Okay, so that's why I'm doing those things. All right, so if we have to find an essay which is already solved, okay, you don't really have so much to worry about. So from the figure, that is 1.9, the BH curve, okay, we are focusing on cast steel, on that curve. So this is cast steel. We are not focusing on the silicon sheet steel, neither on the cast iron, but we are taking a cast steel. All right, so but this is a BH curve for a steel, and you would also want to maybe consider this and then this as a cast iron and then silicon sheet. Okay, but with our question, we're just focusing on the casting. So if you look at this, the flash density was given to be, for the air gap, was given to be 1 Tesla. So this is your Tesla, flash density, okay, it's measured in Tesla, flash density. So you have 1 Tesla here. So if you trace it to heat, your castle axis, and you trace it down, on the fuel intensity axis, you will record certain value for the fuel intensity axis, okay, which you will need to do your calculation. So that is what we are trying to do here. So the magnetic intensity for the castle, that is HC, in the core material for a flash density of 1 Tesla is given as, or is found out as C70. Okay, so basically, if you trace it, all right, you'll be getting somewhere around C70 or approximately. That's what it is, so that ampere turns per meter. Okay, so it simply means that you can also see your, if you like, fuel intensity as a function of what is measured in 80 ampere turns. Are you there? Why is measured in ampere-turns? Oliver Anati Von D. How do you pronounce your name, Oliver? Oliver Anati or Anati? Yes, Oliver. Oliver, you can't hear me?
It's the magnetomotive force.
Okay. So the MMF, all right? So that's fine. So if the ampere-turns is measured in MMF, then we can say that this field intensity is the same as MMF over. Now we know that our length is measured in meters.
Yes, sir.
So that will be
Somebody's coming in.
L. All right. But also H or MMF is the same as NI. Is that right?
Yes, sir.
Yes, sir.
So N for the number of turns, isn't it? And then I
Yes, sir.
for the current, right?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So all over L. So when you go back to your magnetic circuit studies, these things are things that you have looked at some time back. Okay, so we continue. Yeah, so what we are finding there is 670 ampere-turns per meter. Okay, so if that is given, then you will need to also look at the length, okay, of the flux path in the core. When you take the whole core, what is the length? You see, these parts which is disjointed to this side has a space between it and then the main core itself. That space is what we are calling air gap. But if this place is energized, flux will have to link the whole setup so that it will be able to either cause this arm or this part to close up with a core or pull it away. Okay, all right. Now, if we want to also cause the flux, or not even the flux, if we want to cause this torsion, okay, the vertical section here, if we want to cause it to move and close up so that it can be attached to the main core, what do you have to do to be able to establish that? So I mean, if we want to let this arm to move,
So you have to pass chemistry.
you have to do that.
Pass current trade.
You pass current, and when you pass current, what happens? When you pass current, what happens?
It increases the flux.
So the flux will increase. And once the flux increases, it will cause the movable part to move and we are attracted to the core as if it's a relay circuit. Okay. So in this case, we have to tell the total length of the core. Okay? And by the dimension, we are able to conclude that we'll be getting 0.6 meters because when we sum everything, we're getting 60 centimeters. Okay, so like I was showing you, your 10, okay, over 10 here, 10 there, 10 here, 10 here, okay, 5 here, 5 here, okay, 5 here, 5 here, all right, so more or less everything will become 2 times for the upper limb here in terms of the 5, and then because this limb and then this limb have the same dimension, so times the tens. Okay, the same applies to the vertical section, so that's why we can have this. Okay, twice of the 10. Okay, for one sectional dimension, and then plus twice of the 10. Okay, for the other section, and then twice of the 5 for the first sectional, and then the other section. Okay, so by the time we do that, we'll get 60 centimeters. We will divide it by 100 to get meters. So that is what we get here. Then also you have your magnetic intensity, which is in the air gap. And for that, you have our flux density in the air gap divided by the mu naught. What is our mu naught here? So our mu naught is what?
4 pi times 10 to the power negative 7.
No, what that's the value I've given, but exactly what it is. The mu naught is what?
Permissivity in free space.
Okay, so that is the relative permittivity in free space. Okay, so its value, if we determine it, is going to give us that. Okay, so let's continue. So we're giving our flux density for the air gap as 1 Tesla. So 1 Tesla divided by that, we should be getting that's 795.8 times 10 to the power 3 ampere turns per meter. Okay. All right. So the total MMF required will be this. Okay. So from this expression, okay. Once your magnetic circuit is alive, from this expression, this particular expression, you'll be able to do whatever you want. So once you can recall your magnetic circuit, this thing, you can say that, okay, my MML, if I multiply through by L, MMF, if I multiply through by L, I should be getting MMF should be equal to H times L. Okay, it's a field intensity times the length. Okay, so that is basically what we are indicating here, that the total magnetomotive force required will be this. Okay, plus you have to factor in that of the air gap. Okay, so plus what is happening in the air gap. gap. You see, you have an air gap here, you have an air gap here. So that's why we are having twice of that. Okay. All right. So if we do that, we are going to get 8360 ampere turns, okay, or 8360 ampere turns. Now, if that is the case, like we also indicated that our MMF is equal to Ni, okay, which we know from our magnetic circuits class. So MMF is equal to Ni. So if that is the case, then it simply means that we can okay. All right. A moment, please. Let me see. I touched something on my laptop in there. It's telling me I have to close what I'm projecting. So let me. Okay, so can you see my screen now with the slide as we are doing? Can you see it?
Yes, sir.
Or I have to present it again?
Yes, sir.
You can see, right?
Yes, sir.
Yes, sir.
All right, so let's continue. Thank God it didn't go away. Yeah, so we know that this is the case. Our magnetomotive force is equal to the number of turns times the currents in our core circuit, okay? So we can equate this to the Ni or Ni to this, and then we can find the I, which if we do, we are going to get 33.44 amperes. Okay. So once you know the current, the question actually asks us to find the voltage of the DC. So just in your problem, you are given 5 ohms to be the core resistance. So you just recall your basic Ohm's law, that is V is equal to IR, and then you evaluate those values, then you can get your voltage. Okay, so basically that was what was done here, and we are okay with that, giving us 167.2 volts. Okay, so that is what we are actually looking for, and we can also look at the energy density in the core. Okay. In this case, we have 1 Tesla given to us as the flux density. So it means that from 0 to like 1 Tesla, you integrate. Now remember that we did all these things earlier. Okay, so it's just trying to recall this and then establish. Okay, so in terms of the flux density, we'll have this. Like I explained earlier, this AL is basically a constant. Okay, so what maybe you should be interested in to look at how the field intensity will vary. So you integrate that one. Okay, so basically that is what we have to do here. Okay. So the energy density is given by the area enclosed between the BR. Be careful of the castle. Okay. So if we also look at that, we basically look at that and you see it as a triangle. Okay. That is your flux density as is, and then the field intensity as is. So that when you look at, by the time you trace one and hit the thing and come down somewhere here, what you're getting will look like a triangle. So you would basically can apply this half base times height, okay, concepts for your triangle, and you would be getting this. But when you get that one, okay, for what is his name? Kelly Selassie. You don't have to distract the class. If you have to ask question, let us know you are asking question. Pelumi, right? Pelumi.
Yes, I can see what you're presenting, sir.
You asking a question or
Yeah, I said I can see what you're presenting.
you can see. Oh, so all of you can see or some people can see.
Sir,
So I can see the Keza movies.
You can see the Keza move, but what I'm presenting
No,
you
we
can
can
see.
see the Keza movies.
No, we can see what you're presenting. I can see what you're presenting.
network problem.
Oh,
So we can. So all I can see is all I can see is the mechanical energy conversion.
some people can see. So if one person can see, it means the thing is really
So all I
well.
can see is the mechanical energy conversion slide. That's it.
So we can see how what will it be?
So
The half base times height.
okay, you can see um that is half times b times 8, right?
Yes, sir.
Sir.
Which is equal to 1 over 2 times 1 times 670, right?
Yes, sir.
Yes, sir.
Okay.
That's the last thing we can see.
What is his name? That is Pelumi. Pelumi, you still can't see?
I can see what you just said.
You cannot see. Okay. So let's continue. All right. So with that, we just going to get 335 joules per meter square. All right. Then we can also be looking at maybe the volume of the castle, right? And if we determine the volume also, we'll be getting this meter square. Field energy stored in the core is also giving us this, and we'll basically get 1 joule. All right, so that energy density in the air gap is also giving us this,
Sir,
and we can determine it to be this. All right. So yes,
sir, please, what you are saying now is not showing.
Exactly, it's not showing. Yes, sir. Yes, sir. It's not showing.
I'm not getting
The volume of
what.
cast steel core is given by what you said. It's not showing.
Oh, seriously. Uh, that is the volume of the castle core is given by,
Yes,
that is V.
that particular slide is not showing.
You can see that on your screen. VC.
Yes, sir.
VC of the castle.
No, sir. The last thing we can see is 335 joules per meter cube. That's the only thing you can see. That's the last thing we can see.
Oh, I see. Wow. Could you be that? Okay, let me just test you with this. I have moved to another slide, and on that slide, I have example 1.2. Do you have that on your screen?
No, sir.
No, sir.
No, sir.
Okay. So let me just give us 1 minute.
We have 1.9.
Okay. So the last item you can see on your screen is 335 joules per meter cube, right?
Yes, sir.
Yes, sir.
Oh, okay, I see. All right, so I think I know what is happening. Let me I will stop presenting this and I'll represent so that you can see maybe what it's supposed to be. Okay, so let's try this now. Let's see what will happen. This that's social. Okay. Now it's okay. So, all right. So I am moving the slide. Can you see a new slide? This was
No,
my previous
sir.
slide.
No, sir.
No, sir.
No, sir.
Nothing is showing.
Nothing showing at all.
Yes, sir. Nothing.
Yes, sir.
Nothing is showing. Nothing at all.
All right. So
You are not seeing it too.
let me just engage this stuff.
So it's the previous slide showing now 1.2, example 1.2.
So we can't hear you. Sir, please, we
Sir,
can't
please, you have
hear
turned
you.
off your mic. You have turned off your mic.
Okay, so we can see example 1.1, right?
Yes, sir.
Yes, sir.
Okay, that's fine. So we'll continue with that. So you have 1.2. Can you see that 1.2?
Yeah.
Yes, sir.
Yes, sir.
Yes,
All
sir.
right. I think we are good to go. Okay. All right. Thank God. Okay. So was saying that you could also, in bit of looking for the energy, okay, the stored fluid energy, right? Oh man, a moment, please. Sorry, so I'm back, and we could also determine the stored fluid energy, and we would have to look at the, in terms of the energy stored in the core, okay, and then the air gap. Basically, that's all we are trying to deal with, the core and then the air gap. Okay, so that we will just sum these two energies, and then we will tell the total energy in terms of what we have. Oh, I'm on the pointer. Yeah. What we have. Okay, so basically, when you come back to this, okay, the core, what is happening in the core, and then what is happening in the air gap. That's all we are trying to deal with. Okay. So by the time we are through, we should be getting 20.9 joules, right? So so that's most of the fuel energy stored in the air gap, okay, or is stored in the air gap because the reluctance of the air gap is very large as compared to the iron part, okay? Yeah, I think somebody wants to talk.
Can you explain from the VC again?
Okay, so if we go back, that's the volume of the core, all right, which is, this whole thing is basically looking at what do we call it, the dimension, okay, the dimension of the stuff that you are having. Volume, you will want to look at, as far as the core is concerned, what is the volume of such a figure? Is more or less, you are looking at the length, you are looking at the height, the breadth, okay? So that all we are trying to do is to change this thing into standard units, SI units, to make sure that this is 0.05, okay, 0.1, 0.2, right? Because we're given this one, the air gap, okay, is in millimeters. So you divide this by 1,000, isn't it? To convert it into
Yes, sir.
meters, okay? And if it is centimeters, you divide it by what?
100.
Okay, so basically, that's what, if you divide 10 by 100, what do you get? Is that 0.1?
Yes, sir.
That's 0.1. Okay, so you are looking at, that's
Yes,
what
sir.
I was saying. You are looking at, if you like, the core and then the air gap. Okay, but as far as volume is concerned, you have to consider the length, the height, okay, the breadth, that kind of thing. So basically, that is what, as far as the air gap is concerned, okay, we are looking at, that's why we are multiplying it by this. We are multiplying it by the upper and then the lower, which is also 0.2. So with this, then we also add same thing, okay, the other side, and by the time we should be getting 0.003 meters square. And then you can also
Please,
look
question.
at so basically your field energy in the core
Sir.
is
Sir.
for the core. All right, you will look at what is happening within the core times the volume. So you get 1 joule.
Sir.
Okay, so that's what is happening. All right.
Sir.
Yes.
Sir, please, I don't understand the 0.2 even in the volume.
0.2.
Yes.
I'll ask your question.
Yes, sir.
Okay, you say you don't understand.
Yes, the volume is the height times the length times the breadth, but I don't know how you got the 0.2.
Okay. So we come back to the core. All right. So that if we are looking at maybe 10, right? And then we also look at, you see, it's for the entire Western core. So if we have 10, and then even if we also see our customers 10, know our air gap. You have an air gap here. You also have an air gap here, isn't it?
Yes, sir.
Yes, sir.
Okay. So if you have volume of the whole thing, you must also consider the air gap here and then the air gap here. So that is the reason why we have to introduce, of course, he has given us the air gap length is what do we call it, 5 millimeters, isn't it?
Yes, sir.
So that is 5 millimeters. But the question will it be in totality for this and this, or this 5 millimeters times 2? So that is one thing we also have to look at. But where the 2 is coming from basically is as a result of we having an air gap at the, if you like, the upper part and then the lower part. Okay, so we must factor that in. And so all right, so I'll look at it and let's you appreciate what it is that we have done there. Okay. Basically, if all is done, we'll be able to establish 20.9 joules. As if we go through it step by step, we'll be getting that. All right. And what I was saying is that we also have some stored energy in the air gap. Because you also have some reluctance of air gap, which is very large as compared to the iron parts. Of course, when you take the air gap, you have a reluctance in the air gap, and that will make it that maybe we'll have more energy stored in the air gap. Okay? We'll have more energy stored in the air gap. Now, the reluctance is analogous to resistance, so that how flux is supposed to, if we say flow or link your core, the reluctance will not make it so smooth or quick or easy for it to actually uniformly link the whole system. It would make it like it will resist it. So it will not make the flux uniformly link the whole system like that. So because of the fact that we have reasonable amount of reluctance in the air gap, it's going to make our field energy considerable amount will be stored in the air gap. Okay, so that's what is the last part that we are trying to see. Okay. We also know that BH curve or lambda I curve for air gap is a straight line. Okay. And that would mean that our flux density will be mu naught mu RH, or this, where this one is a relative one. Okay. This one is the absolute value. So or our that flux density is directly proportional to the field intensity. So a practical magnetic circuit of magnetic devices, for instance, relays, motors, generators, okay, to have, for instance, iron parts and then an air gap, okay, like you have done in your magnetic circuit. So the reluctance of your air gap is very large as compared to the reluctance of the iron parts. Because of that, we can neglect the reluctance of iron parts so that our BH or lambda I curve of a practical magnetic circuit may be considered linear. Okay, so because what we are looking at, the reluctance in the air gap is large compared to what you have in the iron part, okay, or the core part. You can see the whole thing as linear. And I think I talk about some, we haven't, no, we are yet to talk about that. We are yet to. That is some linearity in our concept of this magnetic mechanical energy system. So we'll talk about that. But this is also another example. What is of importance for you to understand as far as this thing is concerned, that this is actually electromechanical system that we are dealing with. That is the interaction between the electrical system and then the mechanical system. It is doing so through a medium of, what is the medium we are using here?
Magnetic field.
So that's what we are using. So our interaction with each other, that is in terms of electrical system and then mechanical system, through magnetic field. That is basically what we are looking at. Okay, so that if you would want to maybe gain more understanding, it simply means there will be some source energy. If you take, for instance, the electrical system like we are having, okay, so for instance, this problem, there's a source energy, it causes current to flow. You have some winding, some turns, some coil, and is wound on a core. Once current flows in, you expect to establish magnetic flux. Okay, so once this flux is established, we can use the flux to maybe do some work, like in a relay circuit, to cause some further action to take place, so that either you can energize a coil or de-energize a coil by the state of your circuits. And like I think one of this one, yes, like this, you realize that once this circuit is energized and flux actually links the whole thing, if you increase close up with the core, for it to move, it means that you have done some work. There's some force that actually causes it to move. I hope you are seeing this section 1.5, energy in magnetic system, this figure 1.5.
Yes, sir.
Okay. Yeah, so for it to move, it means that some work has been done, and that work cannot be attributed to force that is available. Okay, so that if you like, work done is equal to what? In our basic. Sorry. So force and distance. So you can't rule out the existence of force if you are going to produce magnetic flux, okay, and it links this armature. Force will come into play. So basically, we are just looking at the electrical system interacting with the mechanical system through magnetic field medium, and some of the product we get is force, and then also work done. And we can also talk about energy, because we are talking about certain time span or period of time that maybe certain things can happen. So we can also talk about energy. So basically, this is the thing that we are looking at. So if we are maybe looking at one or two examples, it's just for us to appreciate what is happening if we are putting mechanical and then electrical system together through magnetic field. So for instance, this one, a relationship has been given. So a relationship between the total flux linkages and the current in the coil of a magnetic circuit is in this figure is given by this. So this is our lambda. Lambda is the flux linkage. So the flux linkage, you really cannot also decouple flux production in this our electromechanical system. Our flux production from the current, they relate, so that if you produce more flux, the tendency that you have more current in the circuit is high. So you would always relate the flux to the current in the whole magnetic circuit. So that's why we can write this expression, or that's why this expression can be seen as valid. That's 6I over twice of the I, which is the current, plus 1 Weber turns. So if this is an expression or a relation, we can determine the energy stored in the magnetic field for 0 to 2 Weber for the lambda, or lambda which will exist between 0 and then 2 Weber per turns, or 2 Weber turns, no Weber per turns. So basically, you have been given a range. So once we're talking about energy, then you can also look at what is happening within certain area, within some time period. Because of that, you would want to integrate. Okay, so what it is here is, this is what we were given. We can express this as this. That is, if you just go ahead and then maybe multiply through by 6i. Okay, so that you have your lambda times 2i plus 1, okay, to be equal to 6i, all right, over 2i plus 1. Okay, so you also multiply 2i plus 1 here. Okay, so plus 1. If you do so, it's better that we cancel this one out. All right, and we can now have our, if you like, our lambda 2i plus 1 equal to 6i. Okay. You can also expand this and make I the subject, and that is what we have here. Okay, so if you expand it, you'll be having 2 lambda I plus lambda, okay, which is going to be equal to, all right, so if you like, 2 lambda I plus lambda, and that will be equal to 6i. So that if we are looking for I, no, you have to first separate. So you have 2 lambda I minus 6i will be equal to, or 6i minus 2 lambda I. Okay, so whichever way, you will come back to the same thing. Are you with me?
Yes, sir.
Yes, sir.
Okay, so we will just make I the subjects, and this is what we are going to get. Okay, so basically that is what it is. Then you want to, if you like, integrate it so that you can satisfy that energy situation. Okay, so this is what I am saying, that your what do we call it? 6i minus 2 lambda I will be equal to lambda. Okay, so that we'll factor out I. Okay, so when you factor out I, you have I into bracket 6 minus 2 lambda, okay, which is equal to 6. What am I writing 6 just like that? So which will be equal to lambda. Okay, so will be equal to lambda. So what we just want is the I. So we make I the subject by dividing 2. Okay, so we have lambda divided by 6 minus 2 lambda. Okay, so that kind of thing. So when you are done, in terms of lambda, you would want to use the given expression. In terms of currents, you want to use what we have just written, or you want to use this one, so that we are asked to determine the energy stored in the magnetic field, so that we are given an idea of the fact that the flux linkage lies within 0 to 2 Weber. Okay, so it's better you just look at it in terms of currents. Okay, so this is a valid situation, so that you just integrate this whole thing. Okay, this is all you just want to maybe integrate. Just integrate basically this, so that you are able to tell the energy. Okay, so this is something we can just integrate, isn't it? By the way, if you want to, you can try it on your own and just compare it to what I have here. Okay, so by the time you finish, you'll be getting this. Okay, so basically, this is what you do anyway. Okay, so it is just trying to understand how the source gave rise to some currently produced flux. Okay, and that is happening in the electrical system, and the flux is produced in the core, which by so doing you will get some work done, some force will be established, some work will be done, and you can also talk about energy that is being stored, okay, in the system. So that is the concept of this whole electromechanical thing. Okay, so we'll be playing around 1 and 2, these issues of stored fluid energy, force, and so on and so forth. Okay, so basically that's what is going to happen. So I want us to look at another concept, which is energy, and then co-energy. Okay, are we together?
Yes, sir.
Okay. So energy characteristics of an electromagnetic system. I guess when I talk, you hear. It's clear, or? Okay.
You're clear, sir.
Yes, sir.
Because I have to relocate so that to hear. Unlike our previous time. Okay, so the lambda I characteristics of an electromagnetic system depends on the air gap characteristics of the magnetic material. Okay, so which is an important statement. That is your lambda I characteristics. The lambda is actually issue with the flux. Okay, the flux linkage, which I also said that it is something relates to current, because the flow of current in the magnetic circuit actually brings about the production of flux, especially in the core, or what do we call it? And if we wound the conductors on the core, it's actually set up flux, which links the entire core. And any, okay, so it's not something that we can be easily justified if we separate it. No, so it's inseparable, the flux and then the current. That's why we keep saying flux. Sorry, the lambda I. The lambda is representing the flux and then the current. So lambda plus and then the current of these are lengths, and then the BH curve. The BH has a flux density, and then the field intensity. How is it? What is the measure of the magnetic flux within certain maybe unit area per some time or within some area? What is the intensity of it? Okay, so these are the things that we can talk about if we are looking at the lambda I characteristics. So we say that the lambda I characteristics are shown, okay, in the figure 1.11 for three values of air gap. So that you can see air gap 1, air gap 2, air gap 3. All right. So increasingly towards the large. The characteristic is essentially linear. So if you have a large air gap, the characteristics basically is going to be linear. Like maybe the problem we're looking at this one. So that if you have large air gap lengths, then what will be the reluctance? What will be the state of the reluctance in the air gap if it's large? Oh, are you there? Okay, you heard my question.
Yes, sir.
You didn't hear my question.
So what's the question?
If you have what will be the state of the reluctance? The state
What will be the what?
of the reluctance. So the reluctance will also be large as well.
The state of reluctance will be large as well.
Okay. That's somewhere. Okay, so let's just continue. Now, so we're looking at some linearity issue. So that if the air gap length is large, the characteristic is essentially linear. Okay, so we have a large air gap length, then we see the characteristics for especially our BH is going to be linear regarding to the lambda I. Okay. So the characteristic becomes nonlinear as the air gap length decreases. Okay. So as the air gap length decreases, we're basically going to have a nonlinear situation. Okay. Now, if we take this, if you like, an increasing air gap length vertically for these three values of air gap lengths with the three, which of them do you say that is linear and why? So the third one. Okay. So why?
Because the air gap length is so large.
The air gap length is increased.
Tell me.
Sir?
What do I say? You seem to be very active in the class. Quite a number of them are not making any. What we call it?
Breaking.
Oluwatobi.
Yes, sir.
You were
Yes,
saying
sir.
something.
Yes, sir. So I said the third
What were
one.
you saying? Sorry?
So I said
The
the
third
third
one.
one.
Okay, so
Yes,
why?
sir.
The third one.
Say, as the region for air gap, the air gap, it has increased than compared to the first and the second one. The region of the air gap has increased.
Okay. Okay. So that's fine. So whether the first and or extremely nonlinear, if you look at the first one, okay, because we have a decrease in the air gap length. Okay. Right. Have I given you? I've not given you any assignment, eh?
Yes, sir.
No.
Yes, sir.
Yes, sir.
Okay. All right. So next week, God willing, we will take quiz, 20 questions, and then I will also give you one assignment. Next
Sir, please
week,
come again.
okay? And next week, I actually will
Okay.
27th of this month. 27th, that is day, month, year. We will take quiz, class quiz, and then an assignment. So that is what I mean. The quiz will just be for 20 minutes or 15 minutes. Okay, so maybe 20 questions. 20 questions. 20 questions for at most 20 minutes. And it will be live. 20 minutes. At most, at least 15 minutes. And then I'll also give you an assignment after the class. So it's just an information.
So please, the quiz, how will it be? Will be
The quiz.
answering them.
Have you taken any quiz in Arabic before?
No, at all, sir.
Yes.
Not everyone actually.
Sir, please, can I finish time again? Sir, can I finish time again?
I am saying that.
Sir, please, your line is breaking.
My line is breaking. You
Yes,
sure
sir.
it's not yours?
Yes, sir.
So not everyone has like when been hiring me.
Okay, I am saying you will take quiz. Next time we meet, and to be the first thing in the morning. Oh, sorry, in the afternoon when we meet. Before we continue the lecture, we'll take the quiz first. Then after the lecture, I'll do an assignment.
Yes, sir.
Yeah. How the quiz will be, don't worry. If the questions come, you will see it and you give an answer, okay?
Yes, sir.
Yeah. All right. I'll say that the quiz online, so that you do it and then you submit it. Once it's 20 minutes, that time up, and you cannot submit it after 20 minutes. So if you like answering the question and submitting it, all in 20 minutes.
So,
Oh, you will submit it.
so
So
it's
please,
more like
are we going to type it and send it?
Also, it's going to be an objective something.
How you do it? How you do it? You know, don't worry. You will know, and you will be able to answer it within the given time.
Yes. Sir.
so. What I don't understand is, are we actually like how we are actually presenting something like how we?
So don't worry. You will know. So don't worry. Okay. So you don't worry.
Yes,
Let's
sir.
continue.
Okay, sir.
So I'll give you the details on the page. Okay. Get all the details regarding the quiz. When you come to maybe your class with every detail that you need. Get it. So it's here. So assignment is here. The quiz, the questions are available. So I'll just guide you how to go about it. Okay?
Yes, sir.
And that form, that is part of our 60% assessment. So we must participate and participate well. Okay, so we are looking at our energy and co-energy. Okay. All right, so for a particular value of air gap length, okay, this energy stored in the field is represented by the area A. So when we take this figure, that's 1.12. Okay. Between the lambda axis, okay, this is the lambda axis, okay, and then you have the curve, which is the lambda I curve, because we are dealing with lambda and then I. Whatever curve we drawn is a curve that is drawn between lambda and then I. It means that you can pick the values of lambda on the lambda axis and then the values of current on the current axis to make a point which is continuously represented, and that's how come we have a curve. That's why we are calling it lambda I curve. Now, for that value in terms of the area is existing between the lambda and then the lambda I curve, okay, which is basically what we have here. And what we have here, we are referring to it as the energy of this our lambda I system. Okay. Then also we have another area B, which is existing between the lambda I curve and then the I axis. So this area or this region is what we also refer to as the co-energy. Okay. So that is the co-energy. and we can actually define it in terms of this. So 0 to I. Okay. And if you also take the energy, it will be certain value or 0 to certain value of lambda. Okay. I, the lambda, when you take that of the energy, like I think we have this, where is it? Is it this one? Are you with me?
Yes, sir. Yes, sir.
Yeah, so what we have done is actually that was what actually the person asked us. We should determine the energy stored, okay, which is 0 to lambda, okay, certain value of lambda, okay, I the lambda. So that's why we have to integrate this, which is as a result of the current component of the relation, okay, and that is the energy. But if we are also integrating from 0 to certain value of the current, okay, lambda di, then that is co-energy, and we normally write it as a prime. So you see, this is prime the field. That's the co-energy regarding the field, and this is energy regarding the field. Okay, so if we integrate it for energy, co-energy, it will be like this. Okay, and like we've seen earlier, if we take for the field energy, it will be equal to certain value of lambda from 0, okay, I, derivative of this. Okay, so basically this will be for the energy and this will be for the co-energy. Okay. Now, so this quantity has no physical importance. Okay, so the question is, why are we even bothered about it? It has no significance. However, it can be used to find force. Okay, so another thing to, so you see, it can be used to find force, which is developed in the electromechanical system. So that is another concept which I think you are familiar with, because I am talking about it. So we will use the co-energy to determine the force in terms of the current, okay, and then also energy in terms of the flux linkage, that's lambda, okay, like half in the figure. So your energy plus the co-energy will give us the lambda I, okay, so that is what it means. So that if the lambda I characteristic is linear, it will mean that our energy will be equal to co-energy. That is if it is linear. For instance, if we come back to this thing, and we have something like that, it is expected that your will be equal to okay, so that is what we are talking about. Are we together?
Yeah, yes, sir.
Yes, sir. Yes, sir.
Sir,
Okay.
Yes, sir.
sir,
So we will have this situation. So if it is this, then it simply means we have a linear situation. However, if your lambda characteristic is non-linear, then it simply means that the co-energy is greater than the field energy. So this figure really, I think by observation, you can conclude that it's what? Are you there?
Say come again.
By observation, this figure, by observation figure, you can conclude that is what?
The co-energy is greater than the energy.
Come again?
Co-energy is greater than the energy.
The energy is greater than the co-energy.
I can't hear you.
The energy is greater than the co-energy.
Energy is greater than co-energy. Is that what you're saying?
No. Co-energy is greater than energy. It is non-linear.
Yeah, so by observation, you can see that the energy is what? You can see the co-energy is greater than
the co-energy
energy. Is that
greater
right?
than the energy, yes.
Energy.
Yes, because of that, it is what? Because of that,
It's not linear.
It is non-linear.
so because of that, it's non-linear. The lambda I relationship is non-linear. Okay.
Say.
Yes.
Say, can there be an instance where the
greater than the co-energy, so that you have something like this.
say can there be an instance where the energy is greater than the co-energy?
Yeah, so you can have an instance like that.
What sort of instance?
So how would you define that instance?
So it will also be a non-linear situation. You have the energy greater than the co-energy. It is only linear when the energy is equal to the co-energy. Okay. All right.
So, is there what instance? The energy.
Your network is bad. So come again.
I said, what sort of instance could energy be greater than energy on non-linear chord?
Yeah, basically you have like we are discussing, okay, a situation whereby you have an air gap, okay, like we're looking at what is the situation where we are creating an increased air gap length, which is actually introducing a linear situation. If the air gap actually is a decreased one, okay, if you have this air gap situation, the tendency that your thing to certain level, okay, to certain level, the tendency that your thing will get to the non-linear in the negative. All right. For instance, if maybe you are looking at this, it means that you are actually having a lot more energy here than the co-energy, okay, which is actually not establishing a balance. Okay, so you could have a situation where your air gap length is such small Okay, but you may not want to neglect it because it still has influence on the system. Okay, so that can also lead to a situation where we have a non-linear in a situation where your energy is, if you like, bigger than the co-energy. Okay, so that can be an issue.
It all depends on the air gap.
Then again,
It all depends on the air gap.
of course, you have a situation where the air gap is determining the linearity and then the non-linearity of the situation. Okay, so that is a major factor in this case, the air gap. Okay, like I think it's here. Yeah, so that your lambda I curve, okay, is going to depend on the air gap length and then the BH characteristics curve. Okay, if you like, the B and then the H, they are actually functions not either directly or indirectly of the flux, okay, the flux, which its strength will also be determined by how much current is available and how much space or how wide the air gap is or how small it is. You know, so they are things that interrelate, but the air gap is a major factor because based on the state of the air gap, we are able to do more work or less work to accomplish our objectives. So basically, that is what the case is. Are you with me?
Yes, sir.
Okay. So where are we? Let me see. Yeah. So also you can talk about some few examples here. All right. You can just look at this. This is a simple example that deals with energy and co-energy, and it actually establishes or explains what we are talking about. Okay. So that if you have a linear situation, like I have drawn this particular line. Okay, this one. You will have this. Okay, the field energy will be equal to the co-energy. Okay, in terms of the field. So that if you solve this problem, first one, okay, it will explain that. Let's see, in the time. So if you like, we can just look at it. The lambda I characteristics of a magnetic circuit are described by the straight line segment shown in figure 1.13. So find the energy and then the co-energy for the magnetic circuits at I point A and then at II point B. Okay, so basically that is what it is. So I think you can just take time and then go through this thing yourself. Okay, it's a simple thing, and you realize that we are basically using the, for instance, OA points from OA. This whole thing is a triangle, so you can just tell what is happening in terms of the area here. Just using a triangle, area of a triangle. Okay, have base times height. When you also come to this place where you are getting to B, like OAB, O to B is not a straight line. Okay, so you realize that where am I on this one? Yeah, so I'm trying to draw from O to B. It's not a straight line. Okay, so there are certain things that come to play so that if you have to talk about O to B, then you must factor in what is happening at OA, the area here, and then add what is going to also happen at AB, the area. Taking into consideration this change from from 1 to 1.2. So you have a change of 0.2, okay, 0.2 from A to B. Okay, so basically, if you are just going through, you should just pay attention to those things. It's a simple thing. Okay, so what else to look at? Another thing. Okay. So field energy and then mechanical force. Also another discussion of interest, okay, based on what we are looking at. A moment, please. All right, so let's continue. I had to make some call Excuse you people. So can we continue?
Of course, sir.
Yes, sir.
All right. So the field energy and then the mechanical force. So that we want to consider this system as we have in the figure. Okay. And we are familiar with this kind of system. So we just maybe the new thing that we would have is we have some reference position and then some spring which is attached to a part that moves, or maybe an armature sort of. So that is basically our new system. So what is movable, one part is immovable, so fixed and then movable. Okay. All right. So the current I will set up flux in the circuits. Okay, so these are flux. As a result of this current, which is going to flow through this, and as it flows through the coil here, it will induce EMF into it. Okay, and by principle, the EMF will be induced into it, and in turn also will set a flux. Okay, it's because of how we coil the whole thing, and the current flows through it. So the flux will also tend to be relative, or will try to be dynamic so that we can have EMF to be induced. Okay. Now, the current I will set up magnetic flux in the magnetic circuit. So the flux links or the flux linkages induces an EMF E in the coil, which is this. Okay. Of course, we have resistance in the conductor. And this resistance does not necessarily mean that we have a physical resistance in the circuit or a physical resistor, let me put it that way, in the circuit. But like I said, as a result of this, that your resistance R will be equal to rho L over A for whatever conductor that you are using. So it will be there. So we can see this one as such. Not necessarily maybe we have, but we can also say that let my I, this I, be at certain value because I need certain magnitude of flux. Okay, certain Weber of flux. So I can use R to tell the states of the current, which in turn will also give me certain amount of flux or proportionate amount of flux. So that also is there. Okay, are you with me?
Yes, sir.
So that is not clear very well.
Okay. Has somebody what I just said? Or what I was trying to...
Please, could you make reference to that I again? That's the current.
Come again?
Could you make reference to the I? That's the current. Could you make reference to it again?
Yeah, so I am saying that this current has the tendency of determining how much of the flux will link the system. So this current, the I here, also has the tendency of determining how much of this current should flow in the circuits. Do you understand?
So you said the R also will determine what?
how much of I fulfill.
Okay.
And this I can be physical resistor, or it can be resistor or resistance as a result of this,
Okay.
because the conductor. Those were the things I was explaining. Are you okay? Can we continue?
Yes, sir.
Physical resistance, or I didn't get the other one.
The conductor, this conductor in which current is flowing to, which we have actually wound on the core, has resistance, and we can represent that with this. Yeah. Okay.
Okay.
Now, so suppose the movable parts move from one position, okay? Say X, all right, to X1. So let's say our reference position was X. So we move from X to X1, all right? At the end of the movement, the air gap will decrease. Okay, so these are air gap, it will decrease. What is going to happen? The lambda I characteristics of the system for these two positions are shown in the subsequent figure that we're going to have. Okay, so this is it. So that basically you have A, B, C, D, okay, which is lambda I axis, and we can have lambda I curve. Okay, so these curves are basically lambda I curves. So from position A, we move to position B. So from position A, we actually are saying that, okay, we have moved from X to X1. Then at position B, we have actually moved from X to X2. So a new position is X2 from X1. Sorry, from X. Then our previous new position was X1 from X. Okay, so basically that is what we are saying. Okay. And with this movement, so like we are seeing, movement from A to B, so the arrow is like this. Okay, so we are moving up. And as we have done so, we can see that on the lambda axis, there is a change in lambda, that is lambda 1 and then lambda 2. Or at position C, we have lambda 2. Position D, we have lambda 1. That kind of thing. But currents remain virtually the same, okay, for that movement. Okay, so that's the description of the whole thing. Now, so that's the figure we are looking at. So we should know that operating points of the system are A when X is equal to X1, B when X is equal to X2. So the current from Ohm's law is equal to I V on R. Okay, that's from V is equal to IR. Make I the subject. You have this. Will remain the same as both the positions in the steady state. Okay, so if that is the situation, then we are having this representation, and if the movable part has moved slowly, the current has remained essentially constant during the motion. For that matter, the operating point moves upward from A to B. Okay? as we have in this figure, right? And we can look at the process in terms of the work done electrically and then mechanically. Okay, so we can look at it. So based on the electrical, okay, we can have the induced EMF times the current, so that if we integrate that will mean that we are looking at lambda to lambda 2, okay, and that's based on our curve, okay. It's nothing but area ABCD. ABCD, these areas where we encounter these small movements, okay, so that we can also let me see, okay, yeah, so we can also look at the field. For what is going to happen in the field is going to be OBC minus OAD. Okay, so these are OB and then C, okay, and these are O, A, and then D. Okay, so we are looking at what is going to be the situation at the field. If we also know that our mechanical system is as a result of the electrical system, but it went through a field or coupling system, so that our output virtually, like we look at from the beginning of this discussion, so that our, if it takes, let it will be equal to D mech, okay, mech plus a D in terms of what is happening in the field, okay. It will be the case, because we see this as our output. Now, if that is the case, then we can say that, okay, our mechanical is basically going to be what we have here, okay, this one, which is this area minus that, okay. Already we know that the field is as a result of this minus this, so this is representing the field, okay. This is the field, so that we can have our mechanical system. So when we do that, for D mech, we are going to have area OAB. Okay, so when you go back to what we have, this is our area OAB, which simply means that our mechanical work done is going to be the area enclosed by OAB, okay, OAB, which is basically what we are looking at. Now, that simply means that if the motion occurs under constant current conditions, we maintain current constant. See, like I was giving you an illustration here. This current, sorry, the resistance there. We basically can use it to maintain certain amount of currents, which will equally produce certain amount of flux. So you can keep this current in a constant check by the state of this R. So you can even make it an R that is serving as a rheostat, okay? So where did I get to? Here. So as variable resistor, so that you can maintain certain value of X, which will give you certain value of current. If the current want to vary, you also change the position of the R, and it will keep the current at a steady state. So we can do that to observe or study what we are looking at. Okay. Yeah. So basically, that's what we are looking at. So that if the motion occurs under constant current conditions, mechanical work done is represented by the shaded area, like we're saying, AB, okay? So that this area is the increase in the whole energy, okay, which eventually establishes our, what do we call it, dW mech to be equal to this, because we are keeping the currents actually constant. So if Fm is the mechanical force, okay, causing the, remember what we are looking at is the fluid energy and then mechanical force, right? If the Fm is the mechanical force, which is causing the differential displacement, dx, okay, let's say that's simple change, and from A to B, and on the lambda axis x1 to, oh, sorry, lambda 1 to lambda 2. You know, if Fm is the one causing it, okay, then we can talk about that differential displacement in terms of the mechanical force to be equal to this. We can just rewrite this as this. And we still can also make Fm the subject, but by doing so, we have to differentiate it. Okay, so it should be a partial derivative. Okay, so that you are looking at the displacement and then the value of the constant, the current. Fortunately and unfortunately, our current is constant. Okay, so we are looking at certain displacement at a constant current. So your displacement is as a result of change in lambda. So lambda actually changes, okay? So that you have lambda 1 to lambda 2. So our new position is lambda 2. So that's why it changes. So that is happening at constant current. So it means that we are partly going to differentiate the parameter lambda. Okay, so that is what we are looking at, okay, here for our displacement x. Okay, so that's what we are looking at. So you can come and look at it as this. If you're also looking at a situation where lambda is constant. Okay, so let's look at it. So now we'll consider that the movement has occurred very quickly. Okay. If it has occurred quickly, it may be assumed that during the motion, the flux linkage has remained essentially constant, as we have in the figure. So if it occurs quickly, then this is what it means. So if it occurs slowly, then what we are saying is that the variation of current is not dominant, but flux actually varies in a slow displacement. If it's quick, variation of flux is not noticeable but that of current can be noticed. So the curve to represent it is what we have here. Okay. Are we together?
Yes, sir.
Yes, sir.
Yes, sir. All right, sir.
Yes, sir. Even time.
Hey.
So our flux displacement is not noticeable. So we assume that it's basically constant, but because there's a quick movement, that will also be seen in terms of maybe the manner in which our current also behaves in the system. Now, like we have in the figure, your operating points, therefore, okay, will move upward from A to B, okay, so that like you have this is actually moving from A to a certain point P, okay, but in the previous one you have A moving to B, okay, so that if our operating point moves upwards from point A to point B, okay, as we have in this figure during the motion. Oh, where? So, sorry, I think I have gone back trying to talk about what we already talked about, making reference to what I'm doing. So this is what actually I'm talking about. That if we have a situation that our system actually moves quickly, okay? If our system actually moves quickly, mechanical work done can be represented by area OAP, okay? So that it will be an area representing the decrease in the field energy for this situation. Because of that, we would have to keep the lambda constant and then we'll partly differentiate the displacement. In this case, if you like, our current. But as we can see from this, O A B or O A P and then B. But what it is that is of interest to us is O A P, this shaded region, which is actually the field mechanical work in terms of what the field is, so that we can have this if we are going to look for the mechanical force. That is this from this expression, if we make Fm the subject, it will mean that we partly have to differentiate those, so that basically we having this. Now, what we'll do is that we'll take some examples, we'll solve, and then we'll appreciate basically what we are actually looking at Well, I think some of the examples, okay, so for instance, this one is actually looking for a mechanical force, okay, and you have an air gap, which is a region where some displacement will take place. And we are maintaining constant currents, okay, which means that in that case, flux will have to be dealt with, okay. So that would there be increase in flux or would there be decrease in flux? Okay, so this is one of such an example which maybe we can talk about the next time we meet. All right, I think it's almost time. Okay, but
Yes, sir.
what I want you to do is just note these following. Three items. Okay, three items. Just note them, see if you can get some meaning. Other than that, the next time I meet you, I will talk about this before we go through this example. Okay?
Yes, sir.
But don't forget, we will do this. I'll give you some assignments.
Okay, sir.
All right. So, please don't go offline. Don't go offline. Hold on. I am doing some attendance exercise. Hold on. Just give me 1 minute. That's all. Hold on. I can see that most of the students